Somehow I started the recording. Oops. Get the camera good. All right. Losing my voice today. Okay, so the beginning of the next chapter, we start by talking about relations. And this is one of the most basic abstractions that we're going to talk about in this class. These are not going away. They're in every section from here on out. So it's very important that you understand what exactly these are. So a relation is just a set of ordered pairs. At its fundamental level, that's all it is, a set of ordered pairs. Now, you've been using relations before, you just didn't think about them as a set of ordered pairs. So some of the relations that you've already been using is like the less than relation. So if we think about the less than relation on the set of integers, then here's some things that might be in there. 1 is less than 2, negative 3 is less than 0, negative 1, 2, 3 is less than 1, 2, 3, 4 is less than 5, etc. And you can imagine similar ways of writing out the divides relation, the subset relation. But a relation doesn't have to capture anything meaningful to you. Here's a perfectly valid relation. What does it capture? What's the idea it captures? Who cares? Who knows? The point is, a relation is just a set of ordered pairs. So there are some special relations that we like to talk about, but a relation in general is just a set of ordered pairs. That's all it is.
Is there any sort of relationship between them for any reason?
A relation is just a set of ordered pairs. That's all. So, for example, we'll eventually talk about functions. Functions are just special types of relations. You know what I mean by an ordered pair? I mean a two-element list.
Mm-hmm.
Now we have some special notation that we like to use with relations. I like to say 1 is related to 2 means that 1, 2 is in the relation R. I like to say 1 is less than 2 means that 1, 2 is in the relation less than. So you've seen this type of notation used for relations all the time. 1 is less than 2. 1 is related to 2 by the less than relation. 1 is related to 2. 1 is related to 2 by the R relation. Okay?
1 is related to 2 because it's related
Because
to 2.
1, 2 is in this relation.
Oh, that's horrible.
1 is related to 2 by the R relation. 1 is related to 2 by the less than relation.
Right.
Good?
Yes.
And so when I say the set 1, 2 is a subset of 1, 2, 3, that means that this tuple, this ordered pair, is in the subset relation. All relations are just sets of ordered pairs. If we want to specify that something is not a member of the relation, we do a line through it. 0 is not related to 3 using the R relation because 0, 3 is not in here. So that's logically equivalent to 0, 3 isn't in this set. 2 is not less than 1 is logically equivalent to 2, 1 is not in the less than relation. You with me? It's just what this notation means. When I put a line through it, when I say 0 isn't related to 3 by this relation R, that means 0, 3 wasn't in R. 0, 3 is not in here. When I say 2 is not less than 1, I mean 2, 1 is not in the less than relation. If I were to list all these things out, 2, 1 wouldn't be in there. That's all it means. So just notation. And then we could use set builder notation to talk about some of these things. So let's look at one more. The less than or equal relation on the integers. You're familiar with that one. Here's a way that we can express it. It can be expressed like this. It's a set of all x, y, where x and y are integers, because we just basically said the less than or equal relation on the integers.
Right.
That's all we're talking about. So it's a set of all x, y, where x, y are integers, and y minus x is a natural number. Now, to help this appeal to your intuition, I made a little side note here. When we say y minus x is a natural number, remember all natural numbers are greater than or equal to 0, so y minus x is greater than or equal to 0. So y is greater than or equal to x. So it captures that idea that you're looking for. Do you see how it captures that idea? Am I just completely losing you? Here's a set of all x, y, such that y minus x is a natural number. And I'm saying that this is capturing the idea that x is less than or equal to y. X is less than or equal to y if y minus x is a natural number. What are all the possible natural numbers? 0, 1, 2, 3, 4, 5, 6. Right?
I guess so.
Where are you guys at right now? Are you just in
First grade.
on another planet?
Kind of. Oh, we're paying.
You're just thinking about that word notation? I don't know. Give me no feedback. So I'm writing out the relation less than or equal. So I want to write all the xy where x is less than or equal to y.
Okay, why did you put it in that form? Because that is confusing.
The set or right here?
The set.
The
Is there
set.
any other way besides that you could do that would make it more?
No.
That's
Not
so
that I know
confusing
of.
to me though.
How would you do it?
I don't know because I don't understand it.
Fair point. Okay. So here's the set that I'm trying to capture. I'm trying to capture the set where all the left-hand elements are less than or equal to the right-hand elements.
Okay.
So something in there would be 2, 2. That's less than or equal.
Right.
Another thing in there would be 1, 5. That works. A thing that wouldn't be in there is 5, 1. No, that's not less than or equal to that.
Right. Okay.
So I'm trying to capture the idea of the less than or equal relationship that you're used to,
That makes sense.
where x is less than or equal to y. That's what I want to be able to say. So it's a set of all xy where y minus x is a natural number.
Yeah, I think that's where you lose me.
Right, so this is the part that should feel weird to you. If I can get you here, then this is what should feel weird.
Okay.
Why does y minus x being a natural number mean that y is greater than x, or x is less than or equal to y? What are all the natural numbers? 0, 1, 2, 3, 4, 5, right? They're greater than or equal to 0.
Would it be negative?
Right.
Yeah, negatives aren't natural. They're integers, but they're not natural.
That. Y minus x.
Yeah, it would be negative. It would be, if y minus x is a natural number, then y minus x is greater than or equal to 0. Plus x to both sides the way that you know how, y is greater than or equal to x, or x is less than or equal to y if I would have flipped it.
Okay.
So you see how this is capturing that idea?
Yes.
Now, why did I just say it's a set of all xy where x is less than or equal to y?
Why not?
Because I'm defining what this symbol means. I can't use it in its definition. I'm saying that this symbol is equal to this set. Right. That's the idea I'm trying to capture. We're defining this relation right now.
That just made my eyeballs so Okay.
So now we have a definition of that symbol. It means this relation. That make sense?
Yeah.
Yeah.
Awesome.
Do
So,
you have the definitions of those? Well, I guess.
you can come up with similar things.
Yeah.
Doesn't matter. The point is to just give you some relations that you already have been working with and just get comfortable with them as a set of ordered pairs. Alright. So, hopefully getting a little bit comfortable with relations. Now we have the notion, or the idea, of a relation on a set. So if R is a relation and A and B are sets, we say that R is a relation on A if R is a subset of A cross A. What's A cross A?
A.
You don't remember the Cartesian product?
Cartesian product. Yeah.
Huh?
It's the set of all ordered pairs of all the numbers in each set.
Yeah, okay, I see.
Okay. So this makes sense? How a set of ordered pairs could be a subset of A cross A? No?
I have
Should
it
we do
right
that real
here,
quick?
Right here.
Let's do an example of that real quick.
I have it right here. I can see.
So pick a set A.
1,
1, 2, 3.
4.
No, don't want to get carried away. Then A cross A is equal to the set 1, 1, 1, 2, 1, 3,
Right, right. Yeah.
2, 1,
Okay, yeah, we got
2, 2. You get it?
We're gonna run over.
All the way to 3, 3. Good? So if I'm going to say that R is a relation on A, to give you an example of one that is that case. 1, 2, 3, 1, 3, 3, 1, 1. There's a relation R. So to say that R is a relation on A is the same thing as saying that every element in its left-hand side is in A and every element in its right-hand side is in A, is the same thing as saying that R is a subset of A cross A. Those are all equivalent ways of thinking about it. Good?
Equivalent.
Logically equivalent. You can think about it either way you want. You don't lose information. I don't know. I don't have a better word.
Okay.
Okay. So, let R be a relation, let A and B be sets. We say that R is a relation on A, provided R is a subset of A cross A. And we say that R is a relation from A to B, provided R is a subset of A cross B. And sometimes when we want to specify where it's from and where it's to, we write R where it's from A to B. We might write it that way. And you've probably seen that with functions before. I don't know. Good? Just means all its left-hand elements are from this set, all its right-hand elements are from this set. That's all it means. That's what we're saying here. If R is a subset of A cross B, what's A cross B? That's a set of all ordered pairs where the left-hand element's from A and the right-hand element's from B. Good? Alright. So, let's look at some examples. A bunch of different relations with these two sets of mine. So I've got A equals 1, 2, 3, 4, B equals 4, 5, 6, 7. And I'm going to just create some random relations and state some properties about them. So let's start with the relation R equal to 1, 1, 2, 2, 3, 3, 4, 4. Notice that R is a relation on A. All its left-hand elements are in A, all its right-hand elements are in A. Or R is a subset of A cross A, if you prefer to think about it that way. And notice that this also captures a relation that you're comfortable with or familiar with. Captures is equal relation, right? 1 is equal to 1, 2 is equal to 2, 3 is equal to 3, 4 is equal to 4.
Oh, yeah.
Okay.
So it captures the idea of is equal on A. Right? Let's look at another one. S. S is equal to the set 1, 2, 3, 2. There's a relation on A. Does it capture any cool idea that we have another way of talking about? Not that I can see, but it's still just a relation on A. Let's look at 1, 4, 1, 5, 4, 7. Notice that all the left-hand elements are in A and all the right-hand elements are in B. So T is a relation from A to B. Or T is a subset of A cross B. Same thing. You see it?
Yeah.
Okay. And there's no reason that we have to do from A to B. We can also do from B to A. So U, which is missing its ending bracket. So if we have U as this relation, 4, 4, 5, 2, 6, 2, 7, 3, notice that all the left-hand elements now are in B and all the right-hand elements are in A. So U is a relation from B to A, or U is a subset of B cross A. And then just because you have two sets doesn't mean your relation has to be on those sets. So we've got B here. B is a relation, 1, 7, and 7, 1. But notice it's not relation on A, it's not relation on B, it's not relation from A to B, it's not relation from B to A.
How?
It's in no way related to our sets. Is 1 and 7 in this set? No, so it can't be from A. Is 1 and 7 in this set? No, so it can't be from B.
Can't it be A to B and B to A?
Maybe
No.
like A union B or something?
Well, we could do that if we wanted. But the point is, just because you have two sets you're talking about doesn't necessarily mean your relation has to be restricted to those sets. You with me?
Mm-hmm.
All right. So, sometimes we want to reduce a relation to just the set we're talking about. So, for example, think about the relation less than. Can we talk about less than with real numbers in general? Yeah, but here we were talking about less than with just the integers. And so if you want to reduce a relation to just a particular set, you intersect it with the Cartesian product of that set with itself. So maybe I'm looking at this relation T, and I say, I want to know what this relation T says about elements only in A. The way I do that is I take T, intersect it with A cross A, and here's what it says about elements only in A. Notice this has elements that aren't in A, this has elements that aren't in A. So we reduce the relation to a particular set by taking its intersection with the Cartesian product of that set with itself. Does that make sense?
I'm still thinking about it.
Well, maybe just let it soak in for a little bit. Is that what needs to happen? Just pause.
Well, hang on.
It's usually what happens.
What are you saying what to?
So what does it mean to reduce the relation?
Right. So to reduce the relation to a particular set is a way of saying,
Like
what does this relation say about
So
the
you're
elements
turning
in just
R
this set?
into A?
Huh?
You're turning R into A?
I'm not turning R into A. Oh, sorry. This R doesn't have to do with this R up here. It's just a random relation.
You're right.
So if I want to know what a relation R says about a set A, I take the intersection of R with A cross A. So for example, look at T. This relation T here, what does this say about A? Notice this isn't in A, this isn't in A. This is the only thing it says that's relevant to the set A.
Okay.
So, T intersect A cross A. This is everything in the relation that was relevant to the set A.
Oh.
Does that make sense? Because it's like, think about the less than relation. The less than relation, we can apply that to real numbers in general. Right?
Okay, but what if you only have A cross A?
What if you only have A cross
Not
A?
like A cross B, B cross A.
Then you only have A cross A, that's fine.
So what's the... This doesn't even make sense.
What?
Reduce relationship, or the relation R to set A, take R
To A set A. Take R intersect A cross A. That means to make so that everything in R only pertains to A, you need to look at this instead of all of R. So when we look at the relation T, for example, and the set A up here, the notion 1 is related to 5 doesn't make sense in A. We don't have a 5. The notion 4 is related to 7 doesn't make sense in A. We don't have a 7. But the notion 1 is related to 4 still makes sense. So T, restricted to A, is just 1 related to 4.
So it's just zooming in, taking a little snapshot.
Yeah, it's just taking a piece of it, the piece of it that you care about.
Why?
Well, we did that just barely with the less than and the integers. Look, less than could be applied to real numbers in general. But if I intersect that with just the integers cross the integers, what am I left with? That gets rid of 1.5 is less than 2.5. 1.5 is less than 2.5 is true for here, but that doesn't apply to the integers. Is this just making it worse?
So what? I have an idea of the cross, but I'm not really sure what it would look like to cross the integers. That'd be like
That's all the ordered pairs of integers.
something. That's like a lot.
Well, yeah. How else can I make this make intuitive sense without using infinite sets? I don't know. I mean, it's a really simple idea. I want to take a relation.
I'm trying to understand it. It's saying, okay, so... See, I can't say it because it doesn't...
What does a relation say?
So what? So pick one of those numbers and that's your main number. So U. So I'm going to pick everything that's in B that's in U.
So if I want to take U and restrict it to what set?
B.
B. Then I take all the elements in U, where both their elements are in B.
So it would just be 4, 4.
So it would just be 4,
That
4.
would be the answer.
Yes.
Okay.
So U restricted to B is just 4, 4.
Okay.
Perfect. Does that clear it up? We feel like we're good?
I feel like you make it so much bigger deal than it is, and then it gets confusing.
I'm sorry, it's only a little deal.
No, it's just that. What's all the freaking symbols and words for? I don't understand.
So that when you see the symbols, you know what they mean.
Right.
Because if you ever need to talk about, in a proof, R restricted to a set, you sure as heck better have this exact symbol right here, or if it's R, this exact symbol right here. Because that's its definition. And so if you have to do a proof with it, that's its definition exactly. It's not something else, it's not something kind of like that. If you just have a lot of words and don't write that out, you're going to confuse me and not get points.
So it's all about confusing the teacher, eh? Or not?
Well, confusing the mathematics community in general. There's a reason that the
Okay,
notation
but why
exists.
couldn't we just always freaking write it out in words?
Because and you're writing a lot of words. That's a lot more condensed.
Yeah, it is.
I don't know. Have you ever tried solving old algebra problems?
No.
What's old algebra?
Old algebra problems before algebra notation was developed. So if you were getting educated 1,000 years ago, then they would ask you a question like, the phrasing of the question would be, what number is 3 times greater than twice 5? Or something like that. And it's very wordy. And then when I give you the algebraic expression, you can figure it out like that. But when you're given all the words, it's a struggle. And that's why algebra didn't develop very far until algebraic notation came along. Then it shot through the roof. Because wordy problems like that, they get messy real easily, especially if you want to ask any type of complex question. I mean, even what we just barely had written up here, trying to capture something like this, 2 to the n minus 1 is equal to trying to capture something like that with just words. Probably pretty difficult. You good? Caught up? Ready to continue?
Yeah.
Yeah? Okay, so now the inverse of a relation. The inverse of a relation is a very simple idea. You take each element in there and you swap places. You swap the left hand and the right hand side for each thing in there. So instead of 1, 2, 3, 2, it would be 2, 1, 2, 3. That's the inverse relation. Just swap all the ordered pairs. So, let's see it in writing. The inverse of a relation R, which we denote by R to the power of negative 1. Notice this isn't an exponent. This is just how we mark the inverse. So, that's how we denote it. Is the set of all ordered pairs x, y, where y, x is in R. We just swap the order of things. So, if R equals this set, 1, 1, 2, 2, 3, 3, 4, 4, what's R inverse?
That's so easy.
It's still just 1, 1, 2, 2, 3, 3, 4, 4. Okay, that one's easy. What about S? S is the order pairs 1, 2, 3, 2. What's its inverse? Just 2, 1, 2, 3. That makes sense? Ooh, got a bubble in my chest. Okay, and then let's notice one more thing about T and U. So remember, T was a subset of A cross B. In other words, everything on the left-hand side of T came from A, and everything on the right-hand side of T came from B. So T was a relation from A to B, and so when you take its inverse now, all the left-hand elements are from B, and all the right-hand elements are from A. So if T was a relation from A to B, then T inverse is a relation from B to A. That make sense?
Mm-hmm.
All right. So that's the new stuff. Now we'll just talk about some properties and do a quick proof. Quick proof The inverse of an inverse just gives you back the relation. If I swap all the elements places and I swap them back, we get back what we started with. So let's prove that real quick. Let xy be a member of this relation. Then yx, when we swap its elements, is a member of this relation, right? And so xy is a member of R. Swap again. Good?
Oh, that's easy to prove.
It is easy to prove. Now let's prove. So we just really showed if something's in here, it's in here. Now we need to show if something's in here, it's in here. Take something in R, xy, then yx is in R inverse, and xy is in R inverse inverse.
So the inverse of the inverse is...
Gives you back the initial relation. Right? Okay. Now let's talk about some interesting types of relations. There's five interesting properties that a relation can have. And so let's make sense of what each of them are real quick, and then we'll do some examples, and then we're done. So the first property that a relation can have is called the reflexive property. A relation is reflexive if every element in the relation is related to itself. So in other words, R here was reflexive because every element in there is related to itself. Does that make sense? Mm-hmm. Okay, that's what makes a relation reflexive. A relation is irreflexive if for every element in the set, it is not related to itself. Always related to itself, never related to itself. Good? Good? Okay. Next one is called symmetric. So if you take two elements, x and y, if anytime x is related to y is related to x, we call it symmetric. We'll get a better feel for these as we go through examples, but just try the best you can to wrap your head around these, and we'll go over a few examples, seeing what properties they have. And then we have what's called antisymmetric. So if for all x, y, and a, if x is related to y and y is related to x, then x and y are equal. If that's the case, we call the relation antisymmetric. And then finally, transitive. If you have three elements, x, y, and z, if x is related to y and y is related to z, then x is related to z.
Doesn't anti mean not? Like not symmetric? Why wouldn't it? Why can't
Some names that come up just are not great names.
What?
Because in the same way that antisymmetric does not mean not symmetric, irreflexive does not mean not reflexive. Seriously. So we'll see that. So let's get comfortable with each of these, going over each of these relations and saying which ones they have. So let's start with the equals relation. Is the equals relation reflexive? In other words, is x always equal to x?
Yes.
Yes. So equals is reflexive. Is it irreflexive?
No.
Is it always true that x is not equal to x?
That's true, but no.
It's not true for the equals relation. It's never true. Right. Let's look at symmetric. If we have x is equal to y, is it true that y is equal to x?
Yeah.
Yes, so it's symmetric. Let's look at this one. If we have that x is equal to y and y is equal to x, do we have that x is equal to y?
Yeah.
Yeah, that one's kind of weird, but yeah. So it's antisymmetric. And then finally, if we have...
So it can be symmetric and anti-symmetric?
Yes, it can. That's what I'm telling you. These two things do not mean...
Okay.
Yeah. It's just names. And then finally, if we have x is equal to y and y is equal to z, do we have x is equal to z?
Yes.
Yes, so it's transitive. So equals was all of these except for irreflexive. Right? Alright, let's look at less than or equal. Less than or equal. Is x always less than or equal than x?
Yeah.
Yes, that's always true. Is x less than or equal to x always false? Or is it true that x is always not less than or equal to x? No. So it's not irreflexive. If x is less than or equal to y, is y less than or equal to x?
No.
No, not necessarily, so it's not symmetric. If x is less than or equal to y, and y is less than or equal to x, is x equal to y?
How can they both be less than each other?
If x is less than or equal to y, and y is less than or equal to x,
Then yeah.
is x equal to y?
Yes.
Yes. So let's get this. And finally, if x is less than or equal to y, and y is less than or equal to z, is x less than or equal to z?
Yeah.
Yeah, so it's transitive. Now let's look at less than. Is x less than x?
No.
No, so it's not reflexive. Is x not less than x?
Yes.
Yes, x is always not less than x.
Because it's always.
Is x less than x? No. Oh, so it's not less than x.
See?
Yes.
Okay.
Got it? So that's the first one that's irreflexive. This was the first one that's irreflexive. We never have 1's less than 1, or 2's less than 2, or x is less than x. If that never happens, it's irreflexive. Does that make sense? Okay, next one. If x is less than y, is y less than x?
No.
No. So it's not symmetric. If x is less than y and y is less than x, then x is equal to y. Now, this is a toughie. This is really weird, so think about that one. You have x is less than y and y is less than x. Does that imply x is equal to y? Huh?
No.
Is that statement true?
No.
It is true. It's what we call vacuously true. False implies anything is always true.
Yeah.
You never have x less than y and y less than x. So this is always false with the less than relation. So false implies anything is always true. That's the weird one. It's going to get you over and over again.
Anything is always true.
Yes. Vacuously true. We'll go over this again and again.
False implies anything is always true.
Yes. So if I have x, y.
No, I understand that, but like, give me like an actual physical example.
If Donnie's a purple elephant, he's king of the world. That statement's true, because I'm not a purple elephant.
Oh.
If Donnie's a purple elephant, then finish it however you want.
I see.
Okay, you see it?
Yeah.
Okay, wonderful.
So in some random case that it would be, then they would be.
Well, remember, less than or equal happen to work nicely.
Right.
Right? X less than or equal to y and y less than or equal to x meant x is equal to y. So in that case, we could have had true here and true there.
Right.
But when it was false, it was still true. Double team.
Okay, next one.
And then transitive. If x is less than y and y is less than z, is x less than z?
Yeah.
Yeah. So it's transitive. All right, let's look at the divides. The divide symbol. Does x always divide x?
Yeah. Yes.
Yes, so it's reflexive. Does x always not divide x?
No.
No, so it's not irreflexive. If x divides y, does y divide x?
Not necessarily.
No. If it's not always true, then the answer is no. Symmetric means this always holds.
Okay.
Right? So if you're saying not necessarily, the answer is no. It doesn't have that property. So the divides relation is not symmetric. If x divides y, that does not mean y divides x. Alright? If x divides y and y divides x, is x equal to y?
Yes. No.
No! 3 and negative 3. 3 divides negative 3. Negative 3 divides 3. 3 is not equal to negative 3. That was actually one of your test questions, I think,
It wasn't.
last time.
Oh, last time.
And then transitive. If x divides y and y divides z, does x divide z?
Yes.
Yes, that's one of the things that you proved. So that's divides. Let's look at another relation. Siblings. Is x always siblings with x? Are you a sibling of yourself?
No.
Oh. Yeah.
This comes out to how do we want to find siblings?
You come from the same mom. Huh.
Have a common parent. Is that the way that we should word that?
Sure. Have the same parent. Well. Yeah, don't do siblings, that's dumb.
That'd be like brother or sister.
common, that's how I would have interpreted it, but I don't know right off the.
Oh, brother and sister. Hmm?
Common parent.
Maybe a sister with yourself.
Okay, but what's a brother and sister?
A male with a common parent, or a female with a common parent. That's a brother and a sister. Anyways, we'll say common parent, so it includes yourself. So, do you have a common parent with yourself?
Yes.
Is that always true?
Yeah. Hopefully.
Yeah. Is it true that you never have a common parent with yourself?
Yes.
So it's not irreflexive. If Jack has a common parent with Jill, does Jill have a common parent with Jack?
Yes. What?
Yes.
Okay, that one was tricky. Alright, let's look at this one. If Jack has a common parent with Jill, and Jill has a common parent with Jack, are Jack and Jill the same person?
No.
No, so it's not anti-symmetric.
Hmm.
If Jack has a common parent with Jill, and Jill has a common parent with Frank, does Jack have a common parent with Frank?
No.
Yes.
No!
Wait, hang on, what?
If Jack has a common parent with Jill, and Jill has a common parent with Frank, does Jack have a common parent with Frank?
Yes.
No.
What?
Let's draw a quick family tree here. Here's Jack, here's Jill, here's Frank.
Oh. Okay, that's a bunch of bullcrap because, yeah.
That's
They literally do have a common parent. How do they not? Oh, because.
so they have the same mom,
Right, yeah.
and then here's the dad of these two. So Jill and Frank have the same dad, Jack and Jill have the same mom, but Jack's got a different dad, and Frank's got a different mom.
I see.
So no, it's not transitive. Alright, let's look at ancestor. Is an ancestor up? Are you an ancestor of yourself?
Yes.
No.
Why?
Not this time.
You're not descended from yourself.
Oh.
Is it true that you're always not descended from yourself?
Yes.
Yes. So the ancestor is irreflexive. If Jack's an ancestor of Jill, is Jill an ancestor of Jack? No, so it's not symmetric. If Jack's an ancestor of Jill and Jill's an ancestor of Jack, then Jack and Jill are the same person?
Yeah.
Yeah, because this is always false.
Yep.
Right.
So false implies anything is true. If Jack's an ancestor of Jill and Jill's an ancestor of Frank, is Jack an ancestor of Frank?
Jack's an ancestor of Jill. Jill's an ancestor. Yeah, so yes.
Yes. So that's trying to get you somewhat comfortable with those 5 relations: reflexive, irreflexive, symmetric, antisymmetric, and transitive. You're going to be doing over and over again. I give you a relation. You say which of these properties it has and which ones it doesn't have. I think like 3 questions on your next test has to do with these exact things.
So we should go memorize all that?
So you should know exactly what those mean. Yes, you should know what it means for a set to be reflexive, irreflexive, symmetric, antisymmetric, and transitive. You're in a lot of trouble come next test if you don't know those things. Does that make sense?
Yeah.
So that's the end of the new material for today. Happy to take any questions you have. Nice short class.
Can we go home?
No. But I'm getting